marginal revenue when Q is equal to 100, we will see when marginal revenue when Q is equal to 100, Q is equal to 100, we will calculate it. This is equal to, we will put the value of Q is equal to 100 in this equation. So this will be 1400 minus 12 into 100, 12 into 100. This is here 1400 minus. So marginal revenue when Q is equal to 100 is 1200. Total cost is given. We have to find the marginal cost. First of all, marginal cost is simply that is dq. Now this is our total cost function. The derivative of constant is 0, so this is here 1500, it is here 0, so that is 80 into 1, that is 80. So our marginal cost is 80. Now marginal cost when Q is equal to 100 is equal to 80. So this is our marginal revenue. See the options now. First option says marginal revenue is greater than marginal cost because 200 is greater than 80. So first option is, this is also true. Third one is marginal revenue is less than marginal cost, which is not the case because marginal revenue is greater than marginal cost. And third option tells us marginal revenue is equal to. Most two options are correct, and the correct answer to this question is option A and B. That is option 1 is the correct answer. Another question that was asked was given the total cost, the minimum average cost at minimum cost occur. We have to see the output level also. Now we can find it by total cost. We have to find, first step is finding the average cost. Now average cost is simply average cost, as we know, is equal to total cost divided by quantity. Total cost divided by quantity, q cube minus 10q square, 10q square, and dividing it by q cube divided by q is q square is 10. Now q square divided by q, it is q plus, now 60q divided by q is 60. So this is our average cost. Now we have to see where will be our average cost minimum. For that, we take the derivative of this average cost and set it equal to 0. So this is to say that we find the critical points. Cost will be minimum where the derivative of the average cost is equal to 0. That means we differentiate this average cost function with respect to quantity. So our average cost is equal to AC with respect to quantity. Now the derivative of q square is 2q, and the derivative of q is 1. So we are with this 10, and the derivative of constant is 0. And we set it equal to 0. We set this equal to 0. Now when 2q minus 10 is equal to 0, that means 2q is equal to 10, or q is equal to 5. So the minimum average cost occurs when the quantity q is equal to 5. So first is we got q is equal to 5. Second is we have to find the minimum average cost. Now minimum average cost will be, that is, so I will write here average cost minimum is equal to, we put the value of q is equal to 5 into the average cost. So we put this value in this variable function, minimum average cost function, that is we put the value of q is equal to 5 in this very function. So we get here that is q square is equal to 5 square. So this is 5 square minus 10 into 5, 10 into q is so I will write 10 into 5 plus 60. Now 5 square is 25, so I will write 25 minus 50 plus 60. Now solving this will give us 25 minus 50 is minus 25. Now 60 minus 25 is 35. So our average cost is 35. That is minimum average cost, and our quantity is 5. So the correct option is the first one. Another question that was asked was what is the value of equilibrium level of income for the data given below for an economy. We are given C is equal to 50 plus 0.8 y subscript D, which is the consumption function, and YD is the disposable income. T is 20%, that is tax rate is 20%, and autonomous investment is 100, and government expenditure is 30, which is autonomous here. First of all, we write the income identity, which is given by Y is equal to C, which is consumption, plus investment, plus government expenditure. Now, we know consumption expenditure is consumption function is given as this is 50 plus 0.8, and YD is disposable income. We know that disposable income is equal to the income minus the tax, that is equal to Y minus tax. The tax rate is 20%. So we will write here 0.2 of Y plus the autonomous investment is 100. So we write here 100, and government expenditure is 30. So we write here 30. So we write this here, that is 50 plus 0.8, and we have here Y minus 0.2Y. This gives us this very relation here gives us the disposable income. So solving this is 50 plus 0.8 Y plus 100 plus 30 is 130, or we can write it as this is 50 plus 130, which is equal to 180. So I will write here 180 plus 0.8 into 0.8 Y is equal to 0.64 Y. Or we can write our Y is equal to this. Now transposing this on LHS, this will become Y minus 0.64 Y is equal to 180. Solving this again, now Y minus 0.64 Y is, that is 0.36 Y is equal to 180. Now 0.36 is equal to, that is 0.36 is equal to 36 divided by 100. Y is equal to 180, or Y is equal to 180 into transposing this will get reciprocated. So this will become 100 divided by 36. Now solving this, now here 36 this is 6 are 36, 6 3s are 18, and this will become here 30. So this is here 30. Now 6 1s are 6, 6 5s are 30, and 5 into 100 is 500. So our equilibrium level of income is 500. So the correct option would be this third one, which is 500. Another question that was asked was, given the production function Q is equal to 10 into L to the power 0.8, K to the power 0.25 MPL and MPK. Now, since this is our production function, to find MPL, marginal product of labor, we differentiate partially this production function with respect to L. That is, dQ by dL gives us the marginal productivity of labor. Now, this will become, here we have 10, we write it as it is. Now, L to the power 0.8, its differentiation is 0.8 becomes the coefficient. Uh, L is same and exponent is 0.8 is subtracted by 1, and we are with this K to the power 0.2. We don't do anything this to this K because we are differentiating with respect to L here. The rules of integration says if we are given y is equal to x to the power n, then dy by dx is equal to this n becomes coefficient and exponent is subtracted by 1. Same rule has been applied here. This 0.8 became the coefficient and this 0.8 is subtracted by 1. This is from the rules of integration. Actually, I have made the videos on that. Now solving this, the 10 into a 0.8 is equal to 8. Now L to the power 0.8 minus 1, that is minus 0.2, and K to the power 0.2. When further solving, this will become 8. L to the power 0.2 can be written as 1 divided by L to the power plus 0.2, and we are with this K to the power 0.2, and it can be written as 8 K by L to the whole power 0.2. Here we know that x to the power minus n is equal to 1 by x to the power plus n. That is why this L to the power 0.2 became 1 divided by L to the power 0.2. It became positive exponent in the denominator. So the first option is correct. That is marginal productivity of labor is equal to this 8 K by L to the whole power 0.2. Now we have to find the marginal productivity of capital. Same rule applies here. So first option is correct. We will see the MPK. What is the value of MPK? So I will delete this here. Now MPK is simply dQ divided by dk. Now we differentiate the given production function with respect to capital O. Now this 10 is as it is L to the power 0.8. It is same because we are differentiating with respect to the K. Now K to the power 0.2, its differentiation will become 0.2 K to the power 0.2 minus 1. By the laws of differentiation, exponent becomes coefficient and exponent is subtracted by 1. So this comes out to be now 10 into 0.2, which is equal to 2. Now we are L to the power 0.8 and K to the power. Now 2 minus 0.2 minus 1 is minus 0.8. When solving, this will become 2 L to the power 0.8, and this K to the power minus 0.8 will become 1 divided by K to the power 0.8, which comes out to be 2 L by K to the whole power 0.8. Because powers are same, we can write this in this form. Now which one is this? MPK2 L to the power 0.k. So option third and option first are correct. That means where are these very combinations A and C? That means this very second option is correct for this question. Another question on mathematical economics was given is, we were given assertion and reasoning. Assertion was, if A is any matrix given by, that is A is equal to this very matrix, then determinant of this very matrix is equal to 0, since all elements in the column second are 0. Since here are all elements 0 in the column second. And a reason was given is Laplace expansion permits evaluation of a determinant along any row or column. First of all, we will see what is the Laplace expansion of this very matrix. The determinant is 0. I will show you how it is 0, and whether it is done by the Laplace expansion method. So we will see. Now, what does the Laplace expansion method is actually? So we will take this very example. We are given the matrix. Matrix A is given as this is 5 minus 1, 5 minus 1 and 1, and 0, 0, 0, and 3, 2, 1. This is our Laplace. This is our matrix. We have to find whether it is determinant is 0 or not. Laplace expansion is a method of evaluating the determinants in terms of cofactors. That is, it simplifies the matters by permitting higher order determinants to be established in terms of lower order determinants. That is, now Laplace expansion of this very third order determinant can be written as, this is written as, the determinant is written as A is equal to, that is equal to A11 multiplying by the cofactor C11 plus. If we are going to evaluate a row first, then this formula is there, A12 multiplying by the cofactor C12 plus A13 multiplying by the cofactor C13. Now here A11 is the element and C11 is the cofactor. How is cofactor found? First of all, if this is the first element, that is A11, we mentally delete the row and the column in which it appears and take determinant of the remaining elements. That is, we are here with 5 multiplying it with by the cofactor 0, 0, 2, 1, 0, 0, 2, 1 plus we have A12 is 0, so we write here 0 and mentally delete the row and the column, this very row and this very column, and take determinant of the remaining elements. Now remaining elements are 5, 1, 3, sorry, it is minus 1, 1, 2, 1, minus 1, 1, 2, 1. This is the method of Laplace expansion. Similarly, we can find the A13 element, which is 3, and take the determinant of remaining elements, which will form the cofactors. Now, here we will see what we have to do. I will write again this very matrix. A is equal to 5 minus 1, 1, 0, 0, 0, and 3, 2, 1. Okay, and here this 5 is the A11 element, A11. This is A12. Similarly, this is A13. This is A21. This is A22. This is A33. A33. Similarly, this is A31. This is A32. A32. And this last is A32, A33. Now we can find the determinant of this very matrix by taking determinant along second column. That is by taking determinant along this very column, this second column. Then determinant is equal to, that is equal to A is equal to, here it is A11. A11 is our 0. And multiply it by the cofactor. Our cofactor will be, we will mentally delete the row and the column in which it appears and take determinant of remaining elements. That is minus 1, 1, minus 1, 1, and 2 and 1, 2, 1. Plus we have this very A22 because we are evaluating along the columns. So we write this very element, that is A22 is here 0, and we multiply it with the corresponding cofactor. Here the cofactor will be, so I will change the color to make it clear. Since A22 we are evaluating at A22, we will delete the row and the column in which this very a22 appears, and take determinant of remaining elements. The remaining elements are 5, 3, 1 and 1. So we are with 5, 1, 3 and 1. Plus we take the third element along the column, that is a32. Our a32 is also here 0. So we again we delete the row and the column in which the third element appears, and take determinant of the remaining elements. Now deleting this very row and this very column, we are with this 5 minus 1, 5 minus 1, 5 minus 1, 3 and 2. So 3 and 2. We don't need to actually write this. We can see here 0 times this determinant is 0, plus 0 times this determinant is 0, plus 0 times this determinant is 0. So the determinant is equal to 0. So we can say, so coming to the question, question was, if A is any matrix given by this, its determinant is equal to 0. Yes, that's true. The reason was Laplace expansion permits evaluation of determinant along any row or any column. So we can use the Laplace expansion to find the determinant. So we take the column here. We take determinant along this very column, second column, and we see that since all the elements are 0, its determinant will be also 0. So I hope I make myself clear. I have actually made, or rather I will make a video on the Laplace expansion also. Another question that was asked, for the Cobb-Douglas production function, Q is equal to a L to the power alpha times K to the power beta. The first option was the coefficient A shows managerial efficiency. That is true in the Cobb-Douglas production function. I will write it here. Q is equal to A L to the power alpha K to the power beta. This A shows the total factor productivity, or the efficiency parameter, or the state level of technology. So option 1 seems correct. Option B is, if alpha plus beta is greater than 1, then the production function exhibits increasing returns to scale. That is, if the sum of exponents is greater than 0, we have increasing returns to scale. That is true also for the Cobb-Douglas production function. Coming to the third, marginal rate of technical substitution for L for K is given by beta K by alpha L. So we will see what is the marginal rate of technical substitution. So we will see, if we are given the Cobb-Douglas production function, Q is equal to A L to the power alpha K to the power beta. Marginal rate of technical substitution, that is M or TS, is equal to marginal product of labor divided by marginal product of capital. That means this is the derivative of marginal productivity of labor, first derivative of this. So we will see what is the derivative here. We will write here A is same. Now the derivative of L to the power alpha, that is equal to alpha will become coefficient L to the power alpha minus 1 and K to the power beta, divided by the derivative of this very function, production function, with respect to K, gives us the marginal productivity of capital. So this is also same. A is same. L to the power alpha is same. And since we are differentiating with respect to K, so this beta will become coefficient. This beta will become coefficient. This beta will become coefficient K to the power beta minus 1. Now further solving this, here A L to the power, so we can write it as alpha a L to the power alpha, L to the power alpha, and L to the power minus 1 times k to the power beta divided by, similarly we are with a L to the power alpha times beta k to the power beta, and we can write k to the power minus 1, which can be written as we can write it as alpha. So I will write it here, alpha a L to the power alpha, L to the power alpha, k to the power beta divided by L whole divided by, because L to the power minus alpha can be written as 1 divided by L to the power plus 1. Similarly, we are here with beta L to the power alpha k to the power beta, k to the power beta divided by k. So I will write here divided by k. Sorry, it is k. Now further solving this, we can see this very thing is our Cobb-Douglas production function. This is also Cobb-Douglas. Sorry, we are here with a also. So this thing is here production function. We can write it as alpha divided by q by L whole divided by beta q by k. Now solving this further, this will become alpha divided by beta, and this will become q divided by L. It is q by L into reciprocating this denominator. This will become k divided by q. Deleting q and cancelling this, and we are with this alpha divided by beta k by L. So marginal rate of technical substitution, I'm sorry if it gets here messy because of the lack of space. So our marginal rate of technical substitution is equal to alpha divided by beta times k by L. But in the question we are told it is beta by alpha, which is not the case. So option second is not correct. The marginal product of capital is given by beta q by L. So we will see it also. Our q is equal to this, then marginal productivity of capital is simply the derivative of this partial derivative of the production function with respect to capital. Now partially differentiating, we are with this a L to the power alpha. Now k to the power beta will become the coefficient k, and beta is subtracted by 1 by the law of differentiation. So we can write it as we can write it as beta L to the power alpha, k to the power beta, and k to the power minus 1. So this is equal to beta. So this whole thing here is our original q. So I will write here q. Now k to the power minus 1 can be written as 1 by k, implies beta divided by, option B is also correct. Option C is not correct. Option B is also correct, and option A is also correct. So the correct combination will be A, B, and D. A, B, and D. That means option 2 is here correct. So this gets us somewhat messy. I will show in full detail. Rather, I have made a video on finding the MPL of the Cobb-Douglas production function, how it is done, or how we find the marginal rate of technical substitution and other stuff. Another question that was asked was, which was the following are Hawking-Simon conditions? First is determinant B is 2, B is determinant 1, I minus A should be positive. Third, determinant I minus A should be negative, and the D part is D option is principal diagonal element of matrix I minus A should be positive. So we will see what actually does the Hawkins-Simon conditions are. First of all, the relation is given by this X is equal to I minus A inverse times D, where D is the final demand. I minus A is called the Leontief input-out matrix or technology matrix. X is the column vector of the output to be produced. Now, the first Hawkins-Simon condition says that the determinant of this the technology matrix or Leontief matrix should be positive. This is true because if we are given a technology matrix, let's say we are given a technology matrix, let 0.3, 0.4 or 0.6. Hawkins-Simon condition tells us if this is I minus A, 0. The first condition is correct. The first option rather is correct. Sorry, the first correct option is not correct. It is only talking about the A. Actually, the determinant of the I minus A, that is, the determinant of this I minus A should be greater than 0. That is, determinant of I minus A should be greater than 0. That means option B is correct. Second option, second condition of the Hawkins-Simon is that the elements on the principal diagonal should be positive. These very elements are called the principal diagonal elements. These should be positive. Here 0.3 is positive, 0.6 is positive. So the elements on the principal diagonal should be positive of a I minus A matrix. That is the diagonal elements of I minus A matrix should be positive. That is true. That means the option principal diagonal elements of matrix I minus A should be positive. This option is also correct. Because the Hawkins-Simon condition says first condition is the determinant of this very Leontief matrix, which is also called technology matrix, it should be positive. Determinant of this and another condition is principal elements of matrix I minus A should be positive. That is the elements on the principal diagonal. If this is a matrix 2, 3, 4, 6, the numbers, these very numbers which are on this diagonal, this is called principal diagonal. The elements on the principal diagonal of a Leontief matrix should be positive. That means option B and D are correct, implies the option 3 is correct in this case.